So this video covers the Chapter 14 quiz. Number 1, what happens when the south pole of magnet A, so this is the south pole of one magnet, is brought close to the north pole of a second magnet? Opposites attract with magnets, so the answer is the two magnets are attracted to each other. Question number 2, what determines the polarity of magnetism when current flows through a conductor? We saw this on the homework. It's the direction the current is flowing. This is the correct answer. Question 3, we also saw on the homework, what determines the strength of the magnetic field when current flows through a conductor? It's the amount of current that determines the strength of the magnetic field. The more current, the stronger the magnetic field. Number 4, 4 amps of current is flowing through a conductor. We then increase the current to 8 amps. True or false? The magnetic field strength increases. That is absolutely true. The more current, the stronger the magnetic field. Number 5, we have this simple circuit here. In the circuit shown, what is the status of any magnetic field around the conductors? So this right here is a switch. This right here is a power source, and this right here is a load. All of these lines are conductors. So we have the voltage supply, but then we have this open switch. Notice that it's open. These areas here are not touching. So that means there's no path for current to flow. There's no current flowing. If there's no current flowing, then there is no magnetic field. Number 6 is very similar, but this time we have a closed switch. So now we have a path for current to flow. If current is flowing, then we have a magnetic field. This answer here is wrong, because the magnetic field is not only just around the load. This answer here is wrong because we know there's a magnetic field. This answer here is wrong because it's saying that there's only a magnetic field around this conductor. We have current flowing through the entire circuit, so there's a magnetic field around basically the whole thing. So the correct answer is there is a magnetic field present. Number 7, again we have another very simple circuit. This is a voltage meter. It's not a voltage source, it's a voltage meter. We have a closed switch, and we have this inductor here. An inductor is basically a coil of wire. And the question reads, in the circuit shown, the inductor is simply a coil of wire. We hold a horseshoe magnet around the inductor such that the south pole, I'm going to try to draw this, I'm not a very good artist at all, but just pretend that that's a horseshoe magnet. And let's say this is the south pole and this is the north pole. And we're holding it such that the south pole is on one side of the coil and the north pole is on the other side of the coil. But we're holding the magnet stationary. We're not moving the magnet. True or false, the voltmeter would show a voltage on its display. There is no cutting action here. We have no applied voltage, so therefore there is no current, and so the answer is false. The voltmeter would not show a voltage on its display. Question 8 is the same exact circuit. Still have a closed switch, we still have a voltmeter, we have our coil, and we have our horseshoe magnet. Again, sorry for my bad drawing. This time we're actually moving the magnet in relation to the coil. So we're literally sort of moving the magnet up and down, for example. So now we do have cutting action, and therefore the voltmeter would, it would show a voltage on its display. And number 9, we've seen this a couple of times now. We talked about it in the lecture video. With a coil of wire, wired in series with conductors and a moving magnetic field present at the coil, there are 3 factors that determine the amount of voltage that will be induced in the coil. They are the number of turns of wire in the coil, it is the strength of the magnetic field, and it is the speed of the cutting action.